this episode, we're going to talk about charts as tools for thinking, not decorations, because the chart you choose can either reveal what is true in your data or quietly hide it. Beginners often default to line charts for anything that has an x-axis and bar charts for anything that has categories, but those habits can create misleading impressions. A chart is basically a question you are asking the data, and if you ask the wrong question, you get the wrong kind of answer even if the chart looks polished. The phrase "reveal truth" matters here because data can contain skew, outliers, missingness, and clumps that are easy to miss when you pick a chart that smooths everything away. Histograms are especially powerful because they show distributions, and distributions are often where the most important story lives. Understanding when a histogram beats a line or a bar is about learning what kind of information each chart emphasizes and what kind of information it tends to conceal. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good way to start is to separate the idea of a trend from the idea of a distribution, because these are different kinds of truths. A trend is about how values change in order, usually over time, and line charts are built to show that. A distribution is about how values are spread overall, regardless of order, and histograms are built to show that. If you use a line chart when the real question is distribution, you can end up focusing on wiggles that do not matter and missing the big shape of the data. If you use a histogram when the real question is trend, you can miss timing patterns like seasonality or sudden shifts. Choosing the right chart is not about memorizing chart names. It is about knowing whether order matters for the question you are asking. Once you get that distinction, your chart choices become more intentional and your conclusions become more reliable. Histograms often beat line charts because many modeling decisions depend on the shape of a feature rather than the order of observations. If you want to know whether a feature is skewed, whether it has outliers, whether it looks like two populations mixed together, or whether it is clustered around a few common values, a histogram gives you that information quickly. A line chart, on the other hand, can hide all of that because it encourages your eyes to follow the path, not the pile. When you connect thousands of points in a line, you can create the illusion of continuity even if the underlying data is clumped or discrete. A histogram forces you to confront how frequently values occur, which is what matters when you are assessing whether a feature is likely to behave nicely for a model. For a beginner, this is a key shift. Often you do not need to see how values move from row to row. You need to see what values exist and how common they are. Bar charts are also frequently overused, and one reason histograms beat bars is that bar charts are designed for categories, not for continuous numeric ranges. A bar chart treats each x-axis label as a separate bucket, and that makes sense for categories like device type or region, where each label is meaningful. But if you turn a numeric variable into many separate labels, like every possible age value or every possible transaction amount, you can create a bar chart that is unreadable and misleading. People's eyes will focus on the tallest bars and ignore the overall shape, and the chart can become a cluttered fence of spikes. A histogram solves this by grouping numeric values into bins that represent ranges, which produces a smoother and more interpretable picture of frequency. The important skill is recognizing when your x-axis represents a continuum and should be binned, rather than treated as a list of discrete labels. Bin choice is one of the most important practical details with histograms, because bins control the resolution of the story you see. If bins are too wide, the histogram can hide meaningful structure, like a small secondary peak or a cluster of extreme values. If bins are too narrow, the histogram can look noisy and random, making you think the data is chaotic when it is not. The goal is to pick bins that reflect a sensible level of detail for the context, which often means experimenting rather than relying on a default. Even without changing anything, you can develop a habit of asking whether the histogram story would change if the bins were slightly different. This habit keeps you from becoming overconfident in a single view and helps you treat histograms as a lens rather than an absolute truth. The key is that the histogram is revealing the shape, but your binning choice determines how finely that shape is resolved. Another reason histograms beat lines and bars is that they help you notice measurement artifacts, which are patterns created by how data is recorded rather than by the phenomenon you care about. For example, if a sensor rounds values to the nearest integer, a histogram can show unnatural spikes at whole numbers. If a field is capped at a maximum, a histogram can show a suspicious pileup at that cap, which could indicate truncation. If a process has a default value when missing, a histogram can show an abnormal spike at that default, which might otherwise be hidden in summary statistics. A line chart might show a smooth-looking path through those values, and a bar chart might make the spikes look like categories rather than artifacts. Histograms make these issues visible because they emphasize frequency and clustering. For anyone working toward reliable models, noticing artifacts early is one of the most valuable benefits of good chart choice. Line charts, however, are still essential when order is meaningful, so the goal is not to replace lines with histograms, but to know what each one reveals. A line chart is excellent for detecting trend changes, seasonality, and sudden jumps, especially in time series. It can show you whether a process is drifting upward, whether there are weekly cycles, or whether an intervention changed behavior. But line charts can also create false confidence because a line implies a relationship between adjacent points, and sometimes those points are not truly connected in a meaningful way. If your data points are independent samples sorted arbitrarily, connecting them with a line invents a story of movement that is not real. This is why a line chart is honest when the x-axis is a real sequence like time, and it is often dishonest when the x-axis is just an index or a sorted list without a real sequential meaning. Temporal thinking and chart choice work together because they both depend on whether order should be respected. Bar charts have a similar honesty rule. They are great for comparing counts or averages across a small number of categories, but they can hide distribution detail inside each category. If you make a bar chart of average response time by region, you might conclude one region is slower, but you might miss that the region has a bimodal distribution where most requests are fast and a few are extremely slow. A histogram of response times within each region would show that shape, while the bar chart collapses everything into one number. This matters because modeling problems often depend on the shape and variability, not just the mean. If you are trying to understand user behavior or system performance, extremes and tails often matter more than the average. Histograms reveal those tails, while bars tend to hide them unless you add additional information like error bars, which beginners often forget. A powerful beginner habit is to pair a histogram with a simple summary statistic view in your head, so you do not let the summary mislead you. If a histogram is strongly right-skewed, you should expect the mean to be larger than the median, and that should change how you describe what is typical. If the histogram shows two peaks, you should be suspicious of using one average to represent the entire feature. If the histogram shows heavy tails, you should anticipate that a few extreme values might dominate some modeling behaviors and some evaluation metrics. This is what it means to choose charts that reveal truth. You are choosing a chart that forces your brain to notice the shape that the model will also experience. When you do this consistently, you become harder to fool, both by the data and by your own assumptions. Histograms also beat lines and bars when you are checking whether a transformation might help, because transformations are mostly about reshaping distributions. If you take a log transform of a skewed feature, the histogram can show you whether the distribution becomes more balanced. If you standardize a feature, the histogram can show you whether it becomes centered and scaled in a way that makes sense. If you cap outliers, the histogram can show you what got compressed and whether you accidentally removed meaningful variation. A line chart might show that values look smoother, but it will not show you the overall distribution shape before and after. A bar chart might show that the average changed, but it will not show whether tails got shorter or whether a second peak disappeared. In other words, histograms are the right tool for judging distribution changes, which is often the heart of feature engineering decisions. There is also a truth-revealing aspect to histograms when you are checking class imbalance or outcome distributions. If your target is numeric, a histogram can show whether most values cluster in a narrow band with a few rare extremes, which affects how you measure error and what kind of model might be appropriate. If your target is binary, a histogram is not the right tool, but the same frequency thinking applies. You still want to know how common each outcome is, because that changes how you interpret accuracy. The deeper lesson is that you should choose charts that make frequency and variability visible when frequency and variability matter to the modeling decision. Many beginner mistakes come from relying on charts that only show central tendencies or apparent smoothness. Histograms fight that tendency by emphasizing the full spread of the data. By the end of this topic, you should be able to explain chart choice as a form of honesty about what you want to learn from the data. Histograms are often the best choice when you need to understand distribution shape, including skew, tails, clumps, and measurement artifacts, because they show frequency across ranges rather than a path across rows. Line charts are best when time or sequence order is truly meaningful, because they reveal trend and seasonality, but they can invent stories if order is arbitrary. Bar charts are best for a small number of categories, but they can hide the variability inside each category and make averages look more informative than they are. Choosing charts that reveal truth means matching the chart to the question, then double-checking that the chart is not smoothing away the very thing you need to notice. When you build this habit, your EDA stops being a gallery of graphics and becomes a reliable way to understand what your data can and cannot support.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.